Well, hello, 2019 Lamplighters. Welcome to our fully flipped mock active learning classroom. Today, you all are going to pretend to be students in a general microbiology class that has already been in session for some time, and that in this particular session, you're going to be diving into the learning about HIV/AIDS. So for my role in all of this, you might have noticed and wondered why I'm using an umbrella. Of course, I do dearly love Pooh Bear, and it has been a little bit slushy rainy out there lately. But this is actually my faculty developer or educational developer umbrella. So what I'm going to do in this vodcast is to put on my umbrella when I'm talking as an educational developer. And anytime that I don't have my umbrella on, you'll know that I'm pretending to be the instructor for this general microbiology classroom. Now remember that a flipped classroom has the goal of allowing students to receive the passive components of class material prior to going to class. For years, we've relied on the classroom for passive instruction, where the professor did demos, lectures, and the student was a recipient of that. A flipped classroom takes that outside of class, so students get that passive instruction before they come to class, maybe in the form of a vodcast, and then that opens up class, of course, for them to practice applying, to practice creating, to practice evaluating, building, and all of those things that are much harder and really do require the help of the instructor. So in our vodcast today, we're going to begin working through some events of instruction. These are Gagne's 9 events of instruction. The first one is to gain attention. Poliovirus is in the news. I thought you all would be super jazzed to know that after talking about viruses last time, this article is literally only 8 hours old, and this is about the World Health Organization and their perspective or outlook on African nations with regards to polio. We talked about how polio is still endemic to 2 countries, Pakistan and Afghanistan. However, in Africa, it's not considered endemic, but this new outbreak is interesting. Remember, we mentioned that vaccines can be given as either the live infectious agent, or they can be given as the inactivated infectious agent. Both cause your immune system to recognize a foreign invader and say, whoa, foreign invader, and create those antibodies and activate those T cells that can help you fight that infection. Now, in Africa, they use the drops to deliver the live virus. And so in this particular case, the outbreak that they're talking about actually is due to vaccine-derived cases, because if someone is not vaccinated and they are exposed to shedding of the vaccine that's live, they can become infected, particularly if they're immunocompromised. So I thought you might be super jazzed to see the virus we talked about last time being in the news. So now that we've gained the students' attention, they're feeling pretty interested by this, we want to stimulate their recall. What were they learning when we left off? I kind of feel like Yoda when I think about this. Already know you that which you need. So recall, when we were talking last time, we looked at different families of viruses, and we talked about how they can have different morphologies, whether those be an enveloped morphology, an icosahedral naked morphology. And here we can see that and remember that poliovirus is in the family Picornaviridae, pico meaning little tiny virus, and it is indeed that, a tiny naked icosahedral virus. Remember, this is the most epically awesome way to enclose space. 20 equilateral triangles that make up that icosahedron. It's the most efficient way to enclose space. And recall that poliovirus encloses one RNA molecule as its genome. Remember that viruses can have a single RNA or a single DNA, a single-stranded DNA. They can have double-stranded DNA or single-stranded DNA as well. In this case, polio poliovirus has a single molecule of single-stranded RNA. Now, it's very similar to and in the same family as the virus that causes the common cold, called the rhinovirus. Now, one thing that we didn't get to last time was to talk about the way in which poliovirus replicates. So let's cut to our awesome iPad program to look at that. As we dive into the replication cycle of poliovirus, I've started by making a cheesy cartoon of the poliovirus, and I want to draw your attention to the virion and show that inside of the virion there is a single-stranded RNA, so ssRNA, single-stranded RNA molecule. And the cells that this virus binds to, remember, those are human nasal, pharyngeal, and gut cells. So if we assume this to be a gut cell, we would call the fecal-oral route of transmission of this virus. And on that gut cell, there are receptors. Now, these receptors are actually something that the cell needs. They're involved in immune function, but the virus, poliovirus, he's a tricky little sucker, is going to totally exploit those receptors for its own gain. So it will bind to one of those surface receptors. It wasn't designed for it, but it's going to exploit it. And now, next thing we know, the endocytosis of the gut cell is going to allow this this virion to come on in to the gut cell. So I'm going to do my best to show endocytosis. There's this nice little fluid-filled compartment that has invaginated, and still are those receptors. But now, of course, the binding has taken place, so we recognize that this is the icosahedral virus with its single-stranded RNA and its capsid and spike proteins. And so now the virus finds itself inside of what will become a low pH compartment called an endosome, and that actually triggers the uncoding of the virus, meaning that the RNA is released. So if you will, then this RNA, and I'm going to try to show that in a different color, gets pushed out of a pore, out of the endosome and into the cytosol of the cell. So now we've got this RNA that has uncoded. And this has a directionality. You might have noticed up here that this is a plus sense. So remember that means that the 5' phosphate and the 3' hydroxyl can be labeled like this. Now, it turns out that, man, poliovirus is such a smooth criminal. It actually has the ability to form some three-dimensional structure in this side of the RNA over here. And by doing that, it tricks the ribosomes of our gut cells into thinking that they should convert this RNA into protein. So yeah, you got it. Translation can occur with the assistance of host ribosomes. So this RNA can, in fact, get translated. Said another way, ribosomes can build protein, and in fact, they build a very long polyprotein. This polyprotein is not functional viral protein, but there's a special enzyme called protease that's like a pair of scissors that can clip up this non-functional protein. It'll look like scissors here. And this protease enzyme cuts those down into 3 functional proteins that will help to build daughter viruses. But of course, there's not very much of this 5' to 3' positive sense RNA. And if the virus really wants to replicate, it has to make more of that. So in fact, that's the other thing that can happen, is that 5' to 3' RNA can serve as the template to make what we call negative RNA. So it can create 3' to 5' RNA. And then that can serve, that double-stranded RNA, that's kept at low levels because the cell doesn't want to see that. The virus wants to keep that from giving it away. So now that 3' to 5' RNA can serve to make more 5' to 3' RNA. So then that can get packaged into daughter viruses as well. So this is how poliovirus replicates and how it acts as such a smooth criminal. Now, what I want you to do is to think about how you can apply this knowledge that you have in class and keep this in a pocket so that you can use it when we get into class. That iPad program that I just used to do the drawing is called Viddle, and it works. It's so slick. It's so easy to draw on it. It's like the best possible whiteboard ever. And additionally, it's very easy to, right after I just made it, I just dropped it to my computer, AirDrop, and it was easy to open, and I can just import it right into Camtasia, which is the video editing program that I use. Now that we've reactivated our knowledge about viral families and virion morphology, and we've begun to dive into viral replication cycles, we can turn our attention to the main focus of our active learning for today. We are going to be talking about a subject that is very near and dear to my heart. It is a multi-dimensional subject, and we are going to consider all interdisciplinary considerations of the human immunodeficiency virus, the virus that causes acquired immune deficiency syndrome. And as we ready for that, it's important for us to think about HIV in a very global and in a very historical perspective. It's considered to be the great pandemic of the second half of the 20th century. I would like to argue that it may still be our greatest pandemic, despite your news feed being flooded with news on Ebola. You can ask me why in class if you would like. The total deaths caused by AIDS-related causes worldwide is now tallied up near 36 million. Each year, approximately 1 million people die of HIV, AIDS-related infections and causes. And in 2017, that tally was at 940,000. In 2016, it was right at 1 million. Some are arguing that perhaps we are seeing the decrease in this. I don't know that I'm ready to believe that yet. So as we move our way forward, we want to begin by looking at the morphology of the virus. This is a cartoon of the virion. It took scientists forever to be able to really accurately draw this cartoon. And even now, we know that because HIV is shifting, morphing, and constantly changing its face, it's like a master of disguise, we still don't 100% have a way to depict what it always looks like. However, researchers in 2006 finally were able to show that the virion is typically a conoid one. So you can see that the proteins surrounding the genome of HIV is more of a conoid one as versus the icosahedral that we saw in poliovirus. You will notice, however, that like poliovirus, the virion of HIV is a positive sense single-stranded RNA molecule. However, the way that it replicates, we're going to find out, is very, very different than the way that poliovirus replicates. You'll also notice that unlike poliovirus, which was considered naked, meaning that it only had the outer protein capsid, HIV is an enveloped virus. That means that it has an outer phospholipid bilayer, just like our cells. Now, wait a minute. Look at that. There's a host-derived protein on this outer phospholipid bilayer. So that tends to make one think hard about where this HIV gets its outer phospholipid bilayer. I bet you can give it a guess. We'll do some modeling of that in our class today. Now, you'll also notice that HIV comes with some other things besides just its genome. That is, it carries some enzymes with it. 3 enzymes, in fact. The first one is reverse transcriptase. And this enzyme, as you might guess, catalyzes the process that's the reverse of transcription. So remember that transcription is the process by which DNA is converted into RNA. So reverse transcription, I didn't think about what that would be. It also carries with it protease. And remember how we talked about polio making one large polyprotein that had to cut up to make its individual functional viral proteins? Well, that's what protease does. And then finally, integrase. Now, wait a minute, integrase, that is something very new. This is an enzyme that allows HIV, once it has formed its DNA, to integrate into the host cell chromosome. So you might look then at the family name of HIV. It's called a retrovirus, or it's in the family Retroviridae. Of course, I once had one of my students make me a model that was showed HIV as a virus from the 80s. You know, that is when we first typified the virus, but that's not why it's called Retroviridae. It is called Retroviridae because it's backwards. That is reverse transcription. So retro actually means backwards. The process of transcription goes backwards. So as you give that some thought, that's going to come into our active learning today. I want to make a note that HIV targets a very specific kind of cell within our body. The very first kind of cell that it typically comes into contact with is an immune cell that lines our mucosal surfaces called dendritic cells. It also impacts T lymphocytes and monocytes. You might be thinking, all in all, oh man, it gets our white blood cells. So this is really a deep irony, right? Because here are the cells that are meant to defend us against foreign invaders, and yet HIV is capable of exploiting those cells. Now, as we look back at the virion of HIV, you notice that it had 2 spikes on its surface. These spikes are called GP41 and GP120. GP120 binds to a receptor on the surface of the target cells. This receptor is called CD4, and then there's actually a co-receptor too called CCR5. HIV is kind of like, I don't know if any of you ever grew up in an old house. And my old house in Leadville had 2 doorknobs in the back door. You had to turn one and then you had to turn the other to get in. HIV is like that. It has to turn 2 doorknobs to get into its host cell. So it has to first, GP120 binds to CD4, but it also then has a co-receptor called CCR5. And sometimes it uses an alternate co-receptor called CXCR4. So it requires the binding to 2 different separate doorknobs in order to get in. So as we think about the way in which HIV targets our white blood cells, one can think about the ramifications of long-time infection with HIV, particularly if its replication goes unchecked. It can very easily cause immunosuppression, and does. I will leave you with these thoughts as we move into today's active learning, or tomorrow, whenever you're watching this, and we will learn so much more about HIV, its replication strategy, and you will synthesize this process and be able to apply it to advanced literature and report out on it.